Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be taking what we now know of how to figure out whether a process is favorable or not by looking at Gibbs free energy and using this to calculate the free energies of reaction. And we're going to be bringing together a lot of big ideas because one of the best ways to calculate the Gibbs of a reaction is by knowing how enthalpy and entropy change for a process. Well, we've actually addressed both of these before, but one of the big things here is you'll notice there is a temperature dependence in the Gibbs. So by convention, most of our Gibbs free energies are actually going to be reported under a standard state condition of 298 Kelvin or 25 degrees C. And it turns out, by convenience, this is often where the temperature for which most enthalpy and entropy values are reported. So our enthalpy of reaction will essentially come from enthalpies of formation for the products and reactants. And again, products minus reactants. Similarly, our entropies are going to come from our third law entropies. So again, worth noting, enthalpies typically come from enthalpies of formation because there is no true enthalpy for a reaction. The same is not true for entropies. So we'll use our third law entropies, again, products minus reactants. And then if we're looking at a standard state reaction, we'll simply use the temperature of relevance. So let's go ahead and use these formulas to talk about how to calculate the free energy of combustion of methane at, again, the room temperature 25 degrees C or 298. So in order to do this, we're going to first calculate our enthalpy and entropy of reaction and then combine them. So for the enthalpy of reaction, again, products minus reactants. One of the big things here is making sure that you account for stoichiometry. Remember, we've got 2 moles of water, so we'll have to double that enthalpy. And we're producing 2 moles of oxygen. So when we're subtracting out our methane and our water, we'll have to double the oxygen. Now, worth noting here that oxygen in this case, because it's an enthalpy of formation, is going to be 0, because the enthalpy of formation for any element in its most stable state will always be 0. And so you might not always be able to rely on being able to look these values up because it may be anticipated, already know what it is. So when we go ahead and find the difference in these energies, we're going to find out that this reaction can generate about 890 kilojoules of heat per every mole of methane or natural gas combusted, which, let's be honest, is a whole lot of energy for a very small amount of material. And this means we've greatly disordered the surroundings. However, what we don't know is what happened to the system. Is it more or less disordered? So it is worth noting, you can always get an idea of what the sign of an entropy of reaction is based on looking at the phases. And I want to draw your attention here to the fact that we're producing 2 moles of liquid instead of gas. So we've got 3 moles of gas coming in, only 1 mole of gas exiting. So we'd expect this reaction to have a negative entropy of reaction because, well, turns out systems like making gas. So when we do this, we can again repeat a similar process now with our entropies of formation, noting how low the entropy of water is, not too surprising, and then subtracting out the entropies of our reactants. Note that since these are third law entropies, oxygen will actually have a real entropy value. So turns out when you tabulate all of this together, you end up generating an entropy of reaction of about negative 243 joules per mole Kelvin. However, one of the things I do like to make note of is that since we're going to try and combine our entropy with our enthalpy, this is actually a fairly convenient place to move our units over from joules to kilojoules. So you can see why we typically use joules. It's a much more natural number to say. However, as we're going to combine enthalpy and entropy, making sure they share the same units is very important. So when we do this, the Gibbs free energy will be simply the enthalpy minus the temperature, again, standard state 298, times the entropy of reaction. Well, when you tabulate all this together, it ends up being a energy of, this reaction ends up producing a usable amount of energy of about 818 kilojoules per mole. It is worth noting that this is less than anticipated by enthalpy. And one of the reasons why is because the system itself becomes more ordered. It has that negative entropy of reaction. So some of that energy has to go into more or less offsetting that penalty. So only part of the original 890 kilojoules of heat will actually be able to be harnessed in a usable form. However, this isn't the only way you can go ahead and calculate an enthalpy of free energy of reaction. While all of these values are very common in a lot of tabulated resources, turns out you can often look up Gibbs free energies of formation inside of many of the same resources. So in this case, all you need to do to find the Gibbs free energy of reaction is take the Gibbs free energy of formation of products minus reactants. And again, a lot of the same rules will apply as for enthalpies of formation. All Gibbs free energies of formation represent the amount of free energy now it takes to form 1 mole of product from the elements in their most stable state. And again, you can typically find these values in many resources pages. However, I want to make sure that you avoid the temptation of trying to calculate enthalpies of formation on your own using the third law entropies, because again, the entropies typically reported are going to be third law entropies and not entropies of formation. So if you do ever want to calculate the Gibbs free energy of formation from an enthalpy of formation, make sure that you first go ahead and do the appropriate calculation to get an entropy of formation, because that is not typically what's reported. So again, be cautious of that if you do try and calculate your Gibbs free energy of formation. So in this case, we're just going to simply go to a nice resource page or book, such as that found in the back of your book, to find the Gibbs free energy of formation for all 4 of our relevant species. Now, this process actually is a little bit more straightforward, because all I need to do is do the products minus the reactants. When we do so, again, make note that since this is a free energy of formation, oxygen, being in its most stable state, will have a free energy of 0. And when we calculate this, we have a very similar value of about negative 800 kilojoules per mole. And the difference here is, again, coming from the different resources. And it's not unusual for the Gibbs free energy of formations in these tables to be a little bit off from the true values, which are much more reliably obtained straight from the enthalpies and the entropies. However, one of the other things I do want to make note of is, again, a method of terminology. This reaction is very negative, and this is often called exergonic. You might not encounter this phrase very often, but it is often used in biology and biochemistry, where they represent a reaction producing energy as exergonic and a reaction requiring energy as endergonic. So this is essentially the free energy version of exothermic and endothermic. So we've just changed thermic with gonic. So again, do be aware of this terminology if you go ahead and look at free energies in other sources. So now we have an idea of how we can calculate the free energies of reaction under these standard state conditions. However, it is also worth noting, making sure we can determine how these free energies will change with temperature. So we'll address that topic next time. Until then, take care.